on my computer. Browse my computer. How does SQL Server store that data type? Boop, boop, boop. PowerPoint just crashed.
Oh boy.
Oh, no.
PowerPoint just crashed while I was trying to select my file. Let's try that again, shall we? I love computers. They're my favorite thing in the world.
So this session is being recorded and will be posted up to our YouTube.
I'm going to do this the other way. I was going to do it through live share, but that is not working. So I'm going to share my screen. So, entire screen. Let's do this thing. Alrighty, everyone. Because I've changed the way I'm sharing, I cannot see the chat. So if you do have any questions while I'm speaking, please feel free to interrupt me. I think you have to do it through the chat, and then one of the co-presenters can get my attention. But please feel free to interrupt me. I have enough content to fill 3 hours because this is one of my favorite topics. And I'm only here for an hour. So if you have questions and we run out of time, I can always share my slides and you can go through them yourselves. And reach out to me on LinkedIn is probably the easiest now because I'm not really on X, formerly known as Twitter, mainly because Elon Musk is South African and I'm also South African. And let's just say I know what he's like. Oh, is this being recorded? I apologize. Hi, I'm Randolph. I work for Microsoft. I'm on the database docs team for Microsoft Learn, and I am in charge of SQL Server on Linux and SQL Server migrations. I also contribute to the installation and configuration content. So you will see my name as a contributor on a lot of articles because I like words. Words are cool. This is me. I am a professional nerd. In other words, I get paid to do geeky things. And as I mentioned, I work for Microsoft. I've been working with the Microsoft stack for many, many years. I came up as a Visual Basic developer back in the day, and I work with C# now as well, SQL Server, of course. And let's get into it. We don't have a lot of time. All right, we're going to do a deep dive today. So your eyes are going to cross over and your brain might fall asleep, but that's okay. You have to ask me questions if you need to know something. So what is binary? Well, binary just means 0 and 1. It's a 2-number counting system. It's base 2, 0 and 1. When you get to 2, you have to go back to into the next column and you start with 1, 0. Then you get 1, 1, and then go into the next column, 100. So that's binary, 2 numbers. A CPU is a hot mess of on-off switches, zeros and ones, bits. Those are called bits. There are 8 bits in a byte, but only by convention. In other words, back in the day, in the early days of computing, bytes could be 12, they could be 14, but we settled on 8. When you copy data from storage, that storage could be a network protocol, it could be a hard drive, it could be wherever. As soon as that's copied from storage into memory, it's copied the same way as it was on disk. And when you copy something from the CPU into memory and back and forth between them, it's always stored the same way. The binary is always presented and stored in the same way as it was in the CPU. So what does that mean? Well, that means it's much easier to copy stuff across. It doesn't have to convert it all the time. It's all binary all the time. What that means is if you were to examine the surface of a magnetic disk, you would see little magnetic on and off or true and false or positive and negative values. It's all binary all the time. We have different ways of representing binary. So we sometimes use conventions like decimal or hexadecimal. Hexadecimal is a base 16 numbering system. So you can represent much bigger binary values in a smaller amount of space. But when we use hexadecimal to represent binary, understand that under the covers, it's all binary. We're just using hexadecimal as a convention. If you don't know what hexadecimal is, imagine counting from 0 to 9 and then going from 10 to 15 using A, B, C, D, E, F. So you can represent the values of 0 through 15 using hexadecimal. So when you see a value like 0xAA, that is the value of 170 represented in a hexadecimal value, so that it just takes up less space when you're looking at it. But If you've ever read a book or heard of a story called Gulliver's Travels, or even watched the movies featuring Jack Black as Gulliver, from that book, believe it or not, there was one group of people who, when they ate their breakfast egg, they would have it the pointy end up, and then the other group had their egg with the pointy end down. I'm not kidding when I say this is how we name things in computer science. There's big endian and little endian, and it's referring to the eggs in Gulliver's Travels. I'm not joking, you can look it up. So what we mean by big endian versus little endian is when we're talking about the most significant bits in a byte. In other words, do we read it from left to right or right to left? And as it turns out, Intel CPUs are byte reversed. You read it from right to left. That is confusing at first. It's confusing at second and third and fourth. You get confused very easily when you have to remember that the bytes are reversed. Because, for example, if you're looking at the first 4 bytes that you know are reversed, and then you look at the next set of bytes that you know are reversed, it's not the whole thing that's reversed, it's just these little segments at a time. It is confusing. If this is confusing, that's okay, that's normal. I have to revise every time I give this presentation, and I've given it 3 or 4 times already. ARM CPUs do both little endian and big endian, but Windows chooses little endian. So if you're using Windows on an ARM CPU, or if you're using Windows on an Intel CPU, bytes are usually reversed. And we're bad at naming things because eggs in Gulliver's Travels, seriously, but here we are. So I decided, instead of thinking about Gulliver's Travels, a book by Jonathan Swift written hundreds of years ago, let's update our references. Let's use Missy Elliott as our example. I put my thing down, flip it, and reverse it. So if you're ever looking at binary and you want to remember which way is up, just think of Missy Elliott. You're welcome. We've spoken about Missy Elliott, we've spoken about eggs. Let's talk about 2's complement. Imagine for the moment that you have a 32-bit value. 32 bits, remember I said there are 8 bits in a byte? 32-bit means that it's 4 bytes, because 4 times 8 is 32. That means you can store in 32 bytes up to 4 point something. The exact value isn't important for what I'm explaining, but you can store up to 4 point something billion different values in that number. But if you want to store positive and negative values, you have to use something called 2's complement to make sure that it stays within that 4-byte boundary, or that 32-bit boundary. So what 2's complement does is it uses the same space that you would use from 0 to 4 point something billion. It divides it in 2 so that you can have plus 2.1 billion and minus 2.1 billion. So when you're looking at an integer value that is signed, in other words, it has a positive or a negative value, it may not go up to 4 billion. It may only go up to 2.1 billion. And that 2.1 billion may ring a bell for some of you who know SQL Server, because there's 2.1 petabytes of space for max server memory. There's a number of these 2.1 billion maximum values for an integer, for example. And the reason is because it has to store the plus or the minus value in that same space. If you really want to get into the nitty-gritty, and we are going to today, 2's complement is the method, the algorithm in computer science and math to subtract the absolute value from the maximum possible value to get the negative value. In other words, if you're going to be storing the value of minus 2 as an integer, you will store it as 0x ff 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 fe. There's 4 bytes here. Remember I said there's four bytes in a 32-bit value. The first segment is the first byte, the second segment is the second byte, third byte, and fourth byte. So all of these together make up a 32-bit value of minus 2. And the reason we're able to get a minus 2 out of that is because we're stacking positive and negative values. Good luck for the rest of the session if your brain is already melting. If you're going to be looking at binary on the disk or in memory, you might be tempted to say, well, I've got this value and I want to see what it's going to look like in binary. So why don't I use the built-in SQL functions of cast or convert, which is basically the same thing, and storing it in a var binary value? Well, you can. There's nothing stopping you from doing that. But in some cases, when you do that cast or that convert, it's not going to look the same way as it does on disk. casting to var binary does not always produce the same output as the stored data type, because sometimes that data type needs to encode some metadata. And an example of that would be the decimal or numeric data type. It's the same thing. You might need to store where the position of the decimal point is. So it would be a little bit wider than you would expect. Sometimes little endian isn't what you see. So if you cast something to var binary and then you look at it on disk, you may see it as little endian in the var binary, or you may see it a different way on disk. So don't rely on those if you're examining binary on disk or in memory. But it is useful for checking your work. So for example, if you're looking for integer values on disk for data recovery, and by the way, data recovery is the reason I know all of this. I used to work as a consultant, and I used my binary examination skills to be able to recover or bring back data from storage that was not accessible using SQL Server. Today, we're going to look at a few data types. As I mentioned, we only got that full hour, including Q&A. And so we're only going to look at character strings, numerics, dates and times, and GUIDs. And if there's time left over, we'll look at SQL variant and bit. So let's jump into some caveats as well. We're only going to look at row store values. We're not going to look at column store. We're not going to look at collations that are not Latin, Latin being the ASCII alphabet plus a few extensions. We're not going to be looking at languages that are in Unicode because we don't have time, not because I don't want to. I think Turkish is one of the most fascinating languages because it looks like it could be Latin alphabet, but it isn't, and it can confuse you very easily. But today we're only looking at Latin collation, row store only. We're also only going to look at uncompressed data. If we look at page or row compression, that is a very different conversation altogether, and we just don't have the time for that. We're also only going to look at in-row data. We're not going to look at large object examination, which is off-row data for varchar max and var binary max. There's just no time for that. But it is a fascinating study, and some of the skills that you would pick up today will be useful in examining that kind of off-row page data. And then also, we're not going to look at the old data types, image and text. If you're still using those, please upgrade. var binary exists, please use it. Everybody get down, this is binary. Let's look at what a data page looks like. I'm sure if you've ever been interested in internals, you may have seen this image before. This is from Paul Randall's website. Paul Randall is the former lead of the database engine team at SQL Server. He was the person who led the team that created SQL Server 2005. He left shortly after 2008 came out, I believe, but his knowledge of the internals of SQL Server are obviously second to none because he was there at the time. I believe I saw a name on this attendee list of a person who knows probably as much, if not more than Paul Randall, and definitely more than me, Martin. If it is the same person who I think it is, but if it's not, then here we are. A data page is 8192 bytes in size. I'm going to use the term kilobyte to mean a factor of 2 or a power of 2. If you think of a hard drive sold in a number of kilobytes or megabytes or gigabytes or terabytes, that's usually a decimal value, but we're referring to binary. So when I say kilobyte or byte or whatever, I'm referring to a power of 2, and I just want you to be aware of that. So a data page is 8 kilobytes or 8192 bytes in size. The page header is always 96 bytes. There are portions of the header page that are not used, the page header that are not used right now in SQL Server, even in 2022. But that's because it's reserved for future use. But a page header is always 96 bytes, which leaves you with 8096 bytes left, 8096 bytes, of which a slot array is at the end of the page. The slot array tells the database engine where the rows begin. So if you've got 1,000 rows, you will have 1,000 entries in your slot array at the end of the page, which is why you're limited to 8,000 bytes when you need to store nchar or nvarchar or similar characters. If you go beyond that 8,000, then it has to store some of that off row. So that's where that 8,000 limit comes from. It's because you can only store about 8,060 bytes on a page of data. All the rest is space for rows, as I've mentioned. So let's do a walkthrough. I'm not going to actually crack open a hex editor. I've already got screenshots of that, and it's much easier if we just look at screenshots because I've highlighted stuff. When you look at a data file in SQL Server, data pages are aligned on an 8 kilobyte boundary. In other words, every 8 kilobytes in a data file in SQL Server is a data page. Now that data page might be an index, it might be data itself, it might be a GAM, which is a global allocation map, it might be an SGAM, it might be any one of these different metadata types, but every single one is always 8 kilobytes in size. In SQL Server 7, so the one after 6.5, that's when the data page size changed from 2 kilobytes to 8 kilobytes. But it has always been 8 kilobytes since SQL Server version 7. As I said, if you're looking at a data page, you can see the actual rows. So how do you know if it's a data page? Well, spoiler, the page type is the first byte in a page header. So when you go and look at that 8K page boundary and you look at the first byte, if it's a 1, 0, 1, then that's data. So if we're looking at the first 96 bytes in a page, the first byte is the data page indicator if it's a 1. Easy so far. Now we go to the end of the page, and this is the slot array. Now, what are all those 21s? I'll hear you asking. I formatted my drive, and when I formatted my drive, it formatted them as 21 as the character for a formatted value, so it's empty space, in other words. And then you'll see at the end of the page, slot array. Now, the first thing you'll notice is that this is backwards. I've got 0060, which is 96 bytes from the start of the data page, but this is backwards, 0060. This is what I meant by little endian and big endian. So little endian, which is what this is it's flipped. This is Missy Elliott in action. The first byte, 0, is on the right. The second byte, 60, is next to it. And that is hexadecimal value, which represents 96. In other words, the first row starts just after the page header, which is 96 bytes. Then the second row starts 171 bytes from the start of the data page. These are all from the start of the data page, which is why they have to be 2 bytes. So 01, 02, blah, blah, blah. So with me so far? So there's 2 rows in this example that I'm using here. Let's jump into data pages. We've done data rows. Let's jump into we've done data pages. Sorry, let's jump into the row itself. So when you're looking at the offset, remember in the previous example here, we said that the page starts at offset 96. So we're going to say, let's look at what the byte at 96 looks like. The first byte is tag A, in other words, the record type, and the second byte is tag B. We're starting with 0 and 1 because we count from 0. 0 is a number. So when I say the first 2 bytes, I don't mean bytes 1 and 2, I mean 0 and 1. And that's going to be a convention going forward. So it might help you with confusion if you're wondering why I'm saying the next 2 bytes, but it's only like 2 and 3 or whatever. Byte 1 tag B is usually 0. You'll only see a 1 when it's a ghost forwarded record. Bytes 2 to 3, in other words, the third and fourth byte in a data row, are the null bitmap offset. In other words, somewhere in this row, there might be null values. Now, this is a performance optimization from the SQL Server database engine. You might not have any null values in your columns, but if you do, they've reserved space for it. And it's just easier to say, are there any null values instead of making the row narrower or wider based on whether there's null values. So there's a special section inside the row in bytes 2 and 3, so the third and fourth byte in a row that says, this is where the null bitmap is. And that might be empty.
Yeah, Randolph, there are a couple of questions.
Go ahead.
So one of them is, can Windows run on ARM?
Yes, Windows can run on ARM. There is an ARM build of Windows that is available for testing. It's not for production. It's definitely not for production. Please don't run it in production, but there is one. There's an emulation layer that they have so that you can run Intel x86 code. And in fact, SQL Server, if you want to run SQL Server on ARM, it's quite complicated to get going because it has to use that emulation layer. It has to pretend to be Intel because there's some assembly code that expects Intel CPUs. So It's not fast, in other words. So Windows itself might be quick, but if you have to emulate any x86 code, it'll slow it down a little. And that's where, for example, the Mac that I'm using, my Mac runs on ARM, and it also has to emulate, but the Rosetta emulation layer is encoded in hardware, so it's a lot faster than some other emulators would be. So it's a good question. And you said there were a couple of questions. Is there another one?
Yes. So the other one is it possible to hide the location bar on the middle of the presentation slide?
That one, I wasn't sure if you were seeing that. Sorry. Yes, of course it's possible. There you go.
Okay, and then also third one is, will SQL eventually run on ARM once Windows runs on ARM, or can it run now on ARM on Linux?
That is an excellent question. I'm going to answer the first one by saying I don't know. Even if I did know, I wouldn't be able to tell you because I work at Microsoft and I know a lot of secrets. I'm going to say I don't know. That is my official response. My unofficial response is I don't know. Maybe if there's enough demand from customers, then they'll do it. But if there's no demand from customers, then they'll continue doing what they're doing right now. Now, to answer the second part of that question, can you run SQL Server on Linux on ARM? Yes. Can you run SQL Server on Mac OS on ARM? Yes, but you have to do it in a container because there's a Docker engine that can do emulation. In Mac OS specifically, Docker released an experimental setting that enables Rosetta 2. I just mentioned Rosetta 2 earlier, which is the hardware layer inside the M-class CPUs that allow you to do Intel translations, and it's pretty good. I can run SQL Server at around the same speed as it used to run on my old Intel-based MacBook Pro. So it's a little slower than you would expect on an M-class CPU, but it is faster than running it in software emulation. So you can run it in a Docker container. Can you run it on Linux? You can run SQL Server on Intel Linux. It's natively supported. It has been since 2017. I mentioned that I run the content area for SQL Server on Linux. Will it run on ARM? If there's customer demand. That's the end of the answer. Any more questions?
No, I buried them all under the carpet, so no problem.
All good. All right, so after the null bitmap offset in a row, you're going to find the fixed length portion of the row, which seems weird. Why would you have the fixed length portion before you even know how many columns there are? That's a good question. And we're going to get to that. So for performance reasons, you may have at one point, maybe you worked with a different database engine that said all of the fixed length columns should go first and then all the variable length columns should go next. And when you structure your data, your tables, you'll put all the ints first and then you'll put your varchars later. You don't have to do that with SQL Server because when it saves it to disk, it does it for you. All the fixed length columns are automatically stored first, and then the variable length stuff is done. You don't have to change the column order or anything like that. Set up your columns the way you want to, let the database engine handle it for you. Table structures are metadata. Let SQL Server's database engine handle how it all stores it for you. Don't micro-optimize. You don't have to. In most cases, the database engine is much, much smarter than you are, and it's smarter than I am. I'm not dismissing your intellect, but I can tell you that SQL Server's database engine storage layer is much cleverer at doing this kind of stuff than we are, so don't think twice about which column order you need. Once the fixed length portion is done, then you get the number of columns. Isn't that weird? It's the way it is. Once you've done the fixed length portion and the number of columns, then you'll get to the null bitmap. Remember I mentioned the null bitmap at the beginning, where it says as a performance optimization, it'll say, if there are any null columns, you'll find that null bitmap at this point in the row. This is that point in the row. Then the next 2 bytes, and I haven't specified how big it is because you might have 2,000 columns and 1,100 of them are nulls. So this will be a little bit wider than necessarily You might think it might be more than 2 bytes. So who knows, right? Then the next 2 bytes are count of variable length columns. So you had count of columns before, and now you've got the count of variable length columns. And that's because it knows that the first columns are fixed length, and now it knows of that total, here's the number of variable length columns. Weird, right? Then 2 bytes per variable length column with the end offset. What does that mean? You may have heard consultants, you may have read it on various blogs and websites and in books that have been written by people who write for Microsoft Press, that would include me, that if you use a variable length column like a varchar or nvarchar, that you may set it to a certain size and you'll never get to that size, but you always need 2 extra bytes. So let's say you have a varchar 200 or a varchar 1000, and you only ever use 50 or 60 or 100 bytes out of that. It's going to use 50, 60 or 100 bytes plus 2. And that plus 2 is what we're talking about here, the 2 bytes per variable column with the end offset, because the SQL Server database engine needs to know where that value ends. So it doesn't know where the value ends based on the context of the column. It needs the column to tell it where it ends so that it can go to the next column. And that's what those 2 bytes are for. So when you create a varchar value, keep in mind that it needs 2 extra bytes. So when you're designing your database and you're designing your tables and you're going to have 10 million rows in that table, if any of those columns are varchar, or if you've got multiple varchar columns next to each other, you need to think of an extra 2 bytes plus however much data those columns are storing per cell, per row. Finally, after all of these things, you get the actual variable column data. So it's complicated. Then at the end, if you're using persisted version store, which is part of accelerated database recovery, if you're using read committed snapshot isolation, if you're just using snapshot isolation, if you're using any sort of row versioning in SQL Server, you need to add on an extra 14 bytes per row. And if you've got 10 million rows in your table, that's going to be 14 megabytes of data that you're going to be adding on just for row versioning. But row versioning is a much better idea than reading with no lock or reading uncommitted data. So storage is cheap. I'd always go with the versioning. All right, let's talk about tag A. Remember I said right at the beginning, you've got 2 bytes at the beginning of the row, tag A, and then the ghost record thing. So what does tag A look like? Well, if I look at my storage layer right now and I read the first byte of a row, it's going to look like this, 0, 1, 1, 1, 0, 0, 0, 0, which is 70. But this is meaningless because, as I said in the beginning, tag A is a bit mask. And because Missy Elliott is in the house, we're actually reading this backwards. So this table shows the stored value 0, 1, 1, 1, 0, 0, 0, 0. This is how it's stored on disk, but you need to flip it around. So it's 0 starting from the right, 1, 1, 1, 0, 0, 0, 0. What does this mean? Well, despite the fact that I work for Microsoft, I don't work on the database engine. And despite the fact that I have access to the SQL Server source code, I've never looked this up. This was all my own work before I joined Microsoft, and it was by reading various sources, including Paul Randall's and SQLundercover.com here, and my own investigations. I don't know what this is here in the last column. I don't know what that represents, but I do know what the middle ones are. I don't know what the 8th position is, and I don't know what the 0th, only Beyonce knows. That's what that means. So reading from the right to the left, because this, remember, is in Little Endian, we don't know what the first one means, but we do know that the second one means row versioning. In other words, if you've turned on row versioning, this will be set to true. That's what that one there is. VL means variable length columns. Does this row have variable length columns? Isn't that a convenient thing to know right at the beginning? So in tag A, when it reads the thing for the first time, if this is a 0, it knows it doesn't have to worry about variable length column. So it can be a little bit more efficient when it's reading the row. NB stands for null bitmap. Does it contain a null bitmap? No, it does not, or yes, it does. If it does not, it doesn't have to look for the null bitmap and figure all of that out. It's a performance optimization. Then the next bytes represent the page type. Yes, page types are data, index, all that kind of stuff. I don't have the full list of them. You can look them up yourself, or you can do it and figure it out yourself. But that's what that represents in tag A. Otherwise, we'll be here for hours. So remember at the beginning of this example, when I started showing you this hex stuff, I said, I've got 2 rows, because at the end of the page in my slot array, I had 0060 and then whatever 171 was. So remember the 21, 21, 21 is me formatting my drive, so you can ignore those. The first 2 rows start here at the 70 and end at the 00. But remember, some of this data may be reversed because of Missy Elliott. So we have to figure out where everything is. The first 2 rows start with the same heading. Well, because we figured out that the tag A, remember tag A, the 70, we figured out where that starts. So this is the first row up to and excluding the start of the 70 here. Then this is the second row, including the 70 all the way to the end. Cool. That's pretty cool, I think. Then we're going to look at the null bitmap offset. Null bitmap starts at 0030. Remember, this is byte reversed. So 0030 is the offset of fixed length, and that is at the end of 48 bytes. In other words, the null bitmap is right over here. Isn't that cool? I think that's cool. Now let's get the column count, which includes, remember I said it's the total column count, and then it subtracts the variable length columns, and that column count is 3. I've got 3 columns in this table. And this is just confirming. And when you see a space in the rows here, that's just the way the hex editor works, so that it's easier to group things together, so it's easier to see. It doesn't mean that it's stored as a 03 on disk. It's binary all the time. One variable length column out of those 3 columns means that 2 columns are fixed length. And remember, the fixed length columns are stored before we know how many columns there are. So let's get the variable length column offset, and here it is. In other words, the 61 bytes to the end of the column for the variable length stuff. So we know that there are 2 columns that are fixed width. We know that there's 1 variable length column, and we know where it ends. So far, so good. The fixed length portion of the row, or everything before the column count, is represented by this binary. I gave you a huge clue at the beginning of this conversation where I said Unicode and Latin and all that kind of stuff. And did you know that in Latin text, if you want to store a space, it is stored as 20. Did you know that? Well, you do now. That's a little clue as to what's coming next. So let's figure out by guessing, simple guesswork, what the first column is and where it is. Now, if you design your SQL Server databases correctly, your first column is probably going to be an integer, which is an identity column. And in most cases, that's going to be obvious from the data that you're looking at. So we do have to make some assumptions because we don't have context. Maybe the metadata is destroyed and we're reading this directly off the disk. So here we have byte reversed, remember, the value 1. It looks like an int to me. Let's look at the next part of this column. Remember, it's fixed width. So we figured out that the first 4 bytes are the int, so we know whatever is left over is the entire second column. I've already given you a clue. 20 is a space. And if you know the difference between ASCII and Unicode, you'll know that Latin text or ASCII text always has blanks in it to represent the empty bytes that help it convert it to Unicode. So it's a blank space here. So we can ignore all of this stuff here because it's Unicode, and we know that 20 is a blank. So it looks like N for Unicode, char 20, because we've gone and counted all of these out. There's 20 byte groupings because Unicode uses 2, 3, or 4 bytes wide. So we can figure that out based on guesswork. It's educated guessing, but it's still guessing. It looks like an N char 20. So now what we need to do is we need to go and confirm what we've guessed. Is that an integer in the first column? Well, to guess that, we would have to look at the next row and see if the pattern repeats and that the next row is a 2. And then we look at the data and here from 3F all the way to 00 and see if it looks like N char text. Now let's go and jump ahead to the variable length column of the row. Remember, we know where it starts and we know how long it is. So that's the first thing that we've already ignored. We've already calculated what all of that is. So now tag A bytes said it was true for versioning. So we can actually ignore the last 14 bytes. Isn't that smart? We know that versioning was enabled from the tag A value, so we can remove 14 bytes from the end of the row. And so whatever is left over is the third column. Cool. I've just spent, what, half an hour, 35 minutes explaining to you how you can do this with the hex editor. There is a better way. Hex editing is useful for data recovery. You can see how data is persisted, but you can also use DBCC page. It's built into SQL Server, and if you want to examine your data, much easier. So let's use DBCC page. All you need to know is the data file that it comes from, and it's usually file 1, because a lot of people store all of their data in the primary file group. Please don't do that, but if you do, it makes it easier for us to find. And the page ID. So remember, it's all on that 8K page boundary. The page ID is what you need to figure out which page you're on, and DBCC page can figure out what's going on inside each page because it already has the knowledge of how SQL Server interprets rows and pages. You need to enable trace flag 3604, which outputs any DBCC output to the interface that you're using, whether that's SQL Server Management Studio or Azure Data Studio or similar. And the easiest way to get the page ID is to use a function called DBCC ind for index. DBCC stands for Database Console Command. Or if you're modern, you can use the DMV, which is dm_db_database_page_allocations. You can use that. I prefer DBCC ind because it's easier to type and I'm lazy. So to use page, you turn on trace flag 3604, so all of the things that it's going to say are output to your interface. You type in DBCC ind with your database name, the table name, and -1 to bring back everything. And then you use DBCC page on the database, the file ID, and the page ID to get the input of what's happening on the page. That's all included in the slides, which I'm going to share with you when you're done. So how are characters in Unicodes, varchars, and nvarchars stored? Always be collation is what I said at the top here because it depends on your collation. Collation, Unicode, and UTF-8 are terrifying. Have you ever heard of a byte order mark? If you have a byte order mark at the beginning of a text file and gets misinterpreted, your English text might be converted into unidentifiable Chinese characters because something went wrong with the encoding. You may have seen that before. That means that it was UTF-8 file or a Unicode file was stored as ASCII, and that's obviously not correct. So when you're working with text files on your hard drive, as well as in SQL Server, you should use at least UTF-8 and probably Unicode. Microsoft used creative code pages in the past for DOS, for backward compatibility with CP/M. Microsoft loves backward compatibility, and you love Microsoft because of that. You know that if you created something in VisiCalc in 1979, it will still work today in Microsoft Excel because code pages and all of that made it possible. Microsoft loves backward compatibility. Thank you, Microsoft. Collation affects not only the sort order of how columns are sorted, but how it's stored as well. And as I mentioned before, a column width is measured in bytes or byte pairs. It's not stored in characters. If you say nvarchar 20, that doesn't mean 20 characters. It means bytes or byte pairs. So after all that stuff about collation, if you're storing a string, it's stored as it is on disk. It's not byte reversed. Always check your collation. If you're looking at text and it doesn't make sense, maybe you're looking at Turkish text and you think you're supposed to be looking at English. If you're using UTF-8 and UTF-16, UTF-8 was introduced with SQL Server 2019. Then always use the N in front of your quotes when you're inserting data so that it is stored correctly. If you don't use that leading N, it's going to store it as ASCII, and that's going to break. XML in SQL Server is actually nvarchar max with some optimizations. And that is why the JSON data type in SQL Server doesn't exist, because it's nvarchar max anyway. So if you're going to store 2 gigabytes, why 2 gigabytes? because an int is positive and negative, and you can only do 2.1 billion options. 2 gigabytes of data can be stored in an XML field. 2 gigabytes can be stored in an nvarchar max field. Don't do that, please. So we've spoken about strings. Let's talk about numbers. SQL Server can store exact, which is tiny int, small int, big int, money, small money, and then you've got and decimal and numeric, and then you've got approximate, which is float and real. So let's talk about integers. There's a bunch of them. That's the byte size. So it'll be 1 byte for a tiny int, which means it can go from 0 to 255. Tiny int, by the way, is the only one that doesn't have the minus in front. Small int stores in 2 bytes with 2's complement. Int is 4 with 2's complement, and big int is 8 with 2's complement. Integers are signed integers except tiny int, which I just said. Values are byte reversed. We saw that in the hex editor where 0, 1, 0, 0, 0, 0 was actually 1 because it was flipped backwards. Small money and money, I bet you didn't know this, are actually stored as int and big int respectively. When you store a small money value and you look at it on the disk, it is the same as if you had stored an integer. Even if you've got a decimal point, doesn't matter because small money and money have got fixed metadata ways of storing them. And so if you know those rules, you can figure out what those values are. Fixed precision numeric and decimal is a very interesting thing. Firstly, numeric and decimal is the same thing. If you create a column called numeric and column B is a decimal type, it's the same thing. Under the covers, you can refer to them however you like. You need to use a precision. In other words, how many decimal places there are after the decimal point. So when we talk about precision, we're talking about the whole value, including the bits before and after the decimal point. And then we've got the scale, which is the total number of decimal places. The scale is an incrementing value, and it does not use 2's complement. In other words, decimal and numeric is different to all the other data types where it actually does use the first byte to represent positive or negative. Why they've done it that way, I cannot answer the question, but that is how it's stored. If you have a decimal value with a different precision and scale to another decimal value, they will look completely different on disk. Here's an example. Decimal 19,4, decimal 15,2, decimal 10,4, and decimal 17,6 will look different. But look what's interesting here. Decimal 10,4 and decimal 19,4 are going to look exactly the same because the scale here is the same. So what is this table showing us? Firstly, the 0x is the sign. These are positive values. So that's what this 0, 1 here is for. If you cast it as a var binary, this is the one example where if you cast something as a var binary, it's going to look different than if you look at it on the storage layer. And here you'll see they're very different. And the reason is the metadata in front is saying, I am storing 19, which is this 13 in hex, and 4. That's what that is. So when you store it as a var binary, it's actually encoding the data type in the beginning of the value. So this is going to take up a lot more bytes sometimes than this. So the value 451319 is decimal. If you have the same scale, will look the same on disk as long as you don't exceed any boundaries. But if you store it as different scales, then the value is going to look very different. That's the key takeaway here. Approximate numerics, probably my favorite headache in SQL Server. Floating point data types. What's the time? Let's see. We've got 15 minutes left. I think I can manage to cram this into 15 minutes if I'm lucky. I'm only slightly kidding. A floating point or a real, which is also a floating point data type, stores the closest approximation of an amount as a binary fraction. I'm letting that sink in. It stores the closest approximation of the amount stored as a binary fraction. Now we're going to melt your brain a little. It doesn't use 2's complement. Remember how decimal and numeric uses 0, 1 for a positive number? In float and real, it uses a 0 for positive and 1 for negative. Got that so far? This is amazing. It's great for exponents and terrible for financials, because if you're using approximations of decimal places, it's going to round up or round down to the nearest binary value. And so it's not going to be accurate. Please don't use floating point values for financials. What is a floating point value? Double. Have you heard of double? If you're using double in your C# code, stop, unless they're for scientific exploration. Please don't use floating and real data types for financial calculations. Please don't. I'm going to show you why now. How does SQL Server store a floating point value? 4513.19, which is the same value I used in the decimal example, is stored as something in binary. I've highlighted 3 bytes. Remember Missy Elliott, this is reversed. So it's actually, I'm looking at 0x to start the fact that it's a hexadecimal value, 40B. That is translated into one with lots of zeros, 1011. Why do I care about the first 3 bytes of a floating point value? That seems arbitrary. Well, that's easy. Easy. The 0 at the beginning means it's a positive value, and then the rest of this is the exponent. Is anybody good with a calculator? If you work this out, it's the exponent of this value, but it's not going to be 2 to the power of whatever, which is the closest to 4513. No, that would be too easy. There's something called a bias. In other words, it's a fixed power of 2 of 1023 for float and 127 for real. What does that mean? Well, you have to calculate the bias along with the exponent to get the 4513. Okay, so how does that look? Well, the exponent is a power of 2. So if you take that this number here is 1035, and 2 to the power of 1035, and then you subtract the bias of 2 to the power of 1023, you end up with 2 to the 12. 2 to the 12 is 4096. If that made no sense to you, that's a standard. That is the standard issued by IEEE for floating point values. To get from 4096 to 4513.19, we need to look at the significand, in other words, what's left over, or mantissa. It's got 2 names. Significand and mantissa is the same thing. The significand is 1.00 blah, 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 blah. The one before the decimal point in the significand here can be left out, and it is. So remember, you've got a floating point value that has 3 magic bytes at the beginning, which is byte reversed, so that 40B story. Out of that, there's a 0 in front, which means it's positive. Then you've got this whole magic number story with the powers and the exponents and the bias. Then you've got some more magic numbers, like this one that gets dropped off here. And then whatever's left over, look at that. I've underlined the repeating fraction. This is a repeating value because it's been rounded. It's been rounded to the nearest binary fraction. This is not an accurate value. So because it's rounded, when you convert this back to a decimal value, it's going to be converted back to whatever the decimal value is closest to this binary fraction. Notice the repeating pattern. If we multiply all this out, and you cannot do this in Excel, by the way, because Excel doesn't have enough decimal places. You cannot do it in a lot of tools because there's just too many decimal places. And in fact, SQL Server only goes up to 30-something, 19 decimal places. And this is more than 19. So I had to write code in C# using a very, very big number to tell you exactly how this multiplies out. And you'll see here, 776, that's a power of 2. This fraction here is a power of 2 as a decimal. And you'll see that it rounds up to 4513.19. But if you go to a small enough decimal place, or if you're multiplying these together, you're going to get rounding errors. Please don't use floating points for financial calculations, please. Okay, that took 6 minutes for floating points. And all I basically told you is not to use them. Dates and times. In SQL Server 2008, Microsoft introduced the DATETIME 2 because they're bad at naming things, and date and time and DATETIME offset. We already had DATETIME and small DATETIME. So since 2008, you've got a quite a good selection of options. DATETIME comes from Sybase, which is the product that Microsoft bought, Sybase SQL Server, and became Microsoft SQL Server. And in version 7 is when they rewrote the database engine, where I mentioned the page size changed and so on. DATETIME and DATETIME 2 are new to SQL Server 2008. DATETIME offset is a function that shows you the offset from a DATETIME, as it's clearly named. William Asif is a person on my team and in the database docs team, and also a co-author. He loves DATETIME offset. It's for UTC and time zones and stuff like that. We don't have time for small DATETIME to tell you why it's horrible. Please never use small DATETIME. It measures according to the nearest minute and rounds up seconds. If it's below 30, it goes to 0, and if it's above 30, it goes up to the nearest minute. It's horrible. Don't use small DATETIME. Data is cheap. You can afford 8 bytes. And in fact, you don't even need to use 8 bytes for a DATETIME, and I'll talk about that now. DATETIME is 8 bytes wide and is not byte swapped. The first 4 bytes are the date, starting at 1900. And they use 2's complement for dates prior to 1900. So that makes kind of sense. You've got 8 bytes. The first 4 bytes are the date. It's not byte swapped. And you can use 2's complement to see if it was before or after the year 1900. Ooh. And obviously, it's the number of days. That's what they're counting out. The earliest possible value for a DATETIME is 1753 because the calendar changed to the Gregorian calendar back then. And anything before that will not be accurate because it's not linked to any particular real thing that actually existed at that time. The last 4 bytes are the time, rounded to 0, 3, or 7. I'm sure you've seen this before. The maximum time you can have in a DATETIME is 11:59 p.m. and 997 milliseconds. You cannot have 999. It just doesn't work. It'll be rounded. Jeff Moden, who's been around longer than I have, explains it this way. In the old days on microcomputers, you measured time in 1/300th of a second. If you round that up, 3.3 gets rounded to 0.03, 6.6 gets rounded up to 0.07. And so when you're looking at the data type on disk, the value of whatever 2 at the end means 7 milliseconds past midnight. Easy. Easy stuff. Come on, folks. Let's talk about date, which is a new data type that was invented by Microsoft, and it is 3 bytes wide. This is the first clue that DATETIME uses more data than it needs to. If a date is only 3 bytes wide, it is byte reversed, and it's the number of days since the year 0. No, it's not the year 0 because the year 0 never existed. Aha, that was a trick. The year 1 is the first year in our calendar. The maximum possible value is the year 9999 because it's only 3 bytes wide. You can store more than 10,000 values in 3 bytes, but why would you? Max value is stored as 3,600,000 and something days because of that. Not because of that. So the 3 bytes allow you to store more than that, but you don't need to because that's the maximum value. Time portion can be between 3 and 5 bytes wide. Here's another clue that DATETIME of 8 bytes may be too wide for what you need. You can store precision. Remember we spoke about, I need to kill my dog quickly. Hold on a second. So time stores precision of 0 through 7 decimal fractions of a second. So if you look at a DATETIME value that has decimal place, like you want to store nanoseconds or milliseconds, that's what that precision is referring to. So if you have a time of 7, that means it has a scale of 100 nanoseconds, which is 10 million possible values in a single second. The chances are very good that you do not need to store at this granularity. You probably don't even need to store a precision of higher than 2 or 3 decimal fractions of a second, 3 being milliseconds. If you want a drop-in replacement of DATETIME using DATETIME 2, you can do 7 bytes for every. So for every time you're using a DATETIME, which has that 3 millisecond latent accuracy, which is not great, if you do a drop-in replacement of DATETIME 2 with 3 decimal places, that will only store 7 bytes per column per row. And now you've saved yourself, for every million rows that you've got, an extra megabyte per column. Isn't that great?
Hey, Randolph, there's about 5 minutes left.
Yes,
4
thank
minutes.
you. Perfect. So date and time 2 smushes date and time together. It's completely byte swapped. It's between 3 and 8 bytes wide. As I mentioned, 3 for date, 3 and 5 for time. And date time 2.3 is a drop-in replacement for date time. It'll save you 1 byte, and it's more accurate. It's down to the millisecond instead of the 3 milliseconds. Here is an example of what date time shows you as stored on the disk. So on the left-hand side, you'll see that the values for the date on the right here, because it's completely byte flipped, are the same for each of these. And it's only the time portion that changes because of the number of decimal places. But you'll see that these numbers make sense how they're stored because it's the accuracy that you're storing here. Date time offset, again, smushes date and time together and then adds 2 extra bytes, which is the difference between UTC and now. And that is because you want to store your local time zone, maybe, and you would do that as a date time offset. I personally prefer to store things as date time 2 on their own and store it as UTC time, but it depends on your system. And you do have the option here of date time offset. The offset uses 2's complement. So as we get into the final stretch, because we don't have time for the SQL var binary that I mentioned, let's talk about GUIDs. GUIDs are universal identifiers. They are 16 bytes or 128 bits. Please don't ever use GUIDs as strings. That would require 36 with char or 72 as nvarchar or nchar. And if you use varchar, you're going to have to add an extra 2 bytes. So please don't store GUIDs as strings. That's just silly. Store them as GUIDs, as unique identifiers, is what they're called in SQL. 16 bytes. Just do that. They're unique with a star across multiple environments and time spans. There's no way to check if they're unique. There's just no compute power that's available to check if they're unique. But the chances of collisions are very low. And you can generate them locally. You don't have to generate them at a central place like a identity field with an integer. You can generate up to 10 million identifiers per second per system. I know that's wild, but that's in the spec. It has to be able to do that. Sort order is interesting because you know what a GUID looks like. It's horrible. It's 6 segments separated by hyphens. 2 of those segments are actually combined into one, and that is the 90 and the 1C here that you can see. The clock sequence low and reserved are combined into this block here. So your time low, your time mid, your time high inversion. Every GUID that has a 4 in this position means it's using GUID version 4, so it's the better one. Trust me on that. If you see a 4 there, that means it's version 4 and it's better than the previous ones. The node here used to be the MAC address, but now it's a pseudo-random value. Version 4 of the GUID standard requires that this is pseudo-random. It used to be the MAC address and the time and whatever, some sort of stuff here, but because people could identify systems from this value, that's why they made it pseudo-random. And in fact, it's this node value that a GUID is sorted on. It ignores all of the stuff here and only sorts on this value. That's why GUIDs seem to be in a random order, but they're not. On storage, byte reversed, byte reversed, byte reversed, not byte reversed, not byte reversed, and definitely not byte reversed because you have to sort on this value. We're at time. Do you want me to talk about this or do you want to go into questions?
Let's just go into questions that way because this is a lunch and learn.
Yeah, happy.
Does all of this apply to the Azure SQL with the
Yes.
default collation?
Yes, the database engine used by Azure SQL is identical to the one used in SQL Server, which is identical to the one used in Azure SQL Edge, which is the one that runs on little devices on the edge, IoT. They're all the same database engine, whether using managed instance, SQL managed instance, or Azure SQL database or SQL Server.
And what happened with the SQL Edge on ARM64?
Not enough customers. That's what happened. There's not enough customers. Microsoft's not going to spend the money to keep something going. If customers show an interest in something, then it'll come back. There's no point in maintaining a product that nobody's going to use. It's a good question. I loved SQL Edge on ARM. I really did. And I could run it on a Raspberry Pi and it was great, but it's not enough customers. The version 1.9 of the Azure SQL Edge ARM container will stay around for as long as it needs to. It's eventually going to be retired, but it's there if you want to use it, because now you can run SQL Server in a Docker container on ARM, so it doesn't matter.
And that looks like all of the questions. I really wanted to thank you, and we really appreciated your time with this lecture and in the internals, and I could see where it could be a 3-hour presentation.
Easily. This is very useful for when you're trying to do data recovery, and I've had to do that. And it's because of this knowledge that I could tell if a RAID array has failed. So if you imagine a RAID 5 array can only have one drive going bad. If a second drive goes bad, then the whole array can be thrown away. And you can see that by knowing how big the stripe set is. So if the stripe set is, say, 256K, you can look for any text file that is bigger than 256 kilobytes, and you can see the random data that's written at the end, and then you can tell if a RAID array has failed. It's very useful stuff.
Whoops, one more question. Vlad has sent in any chances for some official documentation for the DBCC page and the DBCC write page?
Vlad and I have a very interesting interaction on the docs pages already. Vlad has contributed some of the changes to database docs. Vlad, no, it's not going to be documented because it's an undocumented feature, because it's an internal function that should not have been known about. And it's only because somebody blogged about it that Paul had to blog about it, and therefore it doesn't exist officially. And there's also a DBCC read page, which I blogged about based on something that Ewald Kress, who I went to school with coincidentally, Ewald Kress wrote a blog post, but he never published it on SQL on Ice. I published it on my own Born SQL blog, and we speak about how read page works.
Well, that seems to be it. Like I said, we really appreciate your time, and thank you very much for the presentation.
You're welcome. I appreciate the attendance. Thank you very much. And if you have questions, come find me on LinkedIn. I used to be on Twitter, as I said, but I'm not anymore. I do have a Mastodon and Blue Sky account, but those are for me, not for Microsoft. So yeah.
Thanks again. Thank you, Paresh, and thanks, Teo.
Take care. Bye.
Thanks,
See
bye.
you guys. Day off, see you
Appreciate
Thursday
you.
or Friday. Bye.
Bye.
Thanks all.